All right, let's do some more examples of graphing with transformations. Here we've got a couple transformations here. What can be a little bit tricky sometimes is identifying the parent function, but hopefully we see here that the only parent function involved is the squaring function. So our parent function will be y equals x squared. Right, so that's our parent function. If we wanted to, we could draw in the parent function as a reference. Okay, we know it goes through 1, 1. It would go through 2, 4. When we square 2, we get 4. So we have the parent function would look like this. If we wanted the parent function there, we can do that. You don't need to draw the parent function in if you don't want to. But the idea here is when we have x minus 2, the negative, or the subtracting inside, we're inside of the squaring function, right? We would do that before we square. So that's inside the squaring function, means we're going to move horizontally in the opposite direction. So when we subtract 2, that means we're going to move to the right. We're going to move the whole curve to the right 2 units. If I wanted to go ahead and draw that in, that means I move my vertex over here to 2, 0. There's my sort of halfway function. The next thing I'm going to do is move the whole function down 3 units. I'm subtracting outside, so I would subtract the 2, then I square. After I square, I subtract. So that's the last thing I would do, is move the whole function down 3 units. So I'll take this dotted blue curve here and moving it down 3 units. And make sure you take the time to make your points as accurate as you can within reason here. So we get a nice smooth parabola. Mine's pretty bumpy here. It's kind of tough to draw these on a surface, so give yourself some slack, and I will too. But try to make them smooth. Don't get so crazy that you're drawing like these kinds of curves. And just take the time to try to make it look as good as you can. But there's our curve. This solid blue curve is the graph of f of x. Okay, that's f of x. Now in B, they kind of do a fun little twist on us here. They say, well, graph the absolute value of f of x. And this is something totally new probably for most of you. But you understand the concept that absolute value means take negative values and make them positive, right? It's kind of a piecewise function. We're going to talk about that in the next section, piecewise functions. So if, let's say this, if you have a positive value coming from this blue graph, it's going to stay positive when you take the absolute value. But when you have a negative value, when their y-coordinate is negative from the blue graph, that negative has to become a positive value. So it's like this. We're going to take that blue curve and we're going to transfer it over here, and that would be f of x. So let me draw that sort of as our parent graph. I'm just drawing the same f of x that I had from part A, right, because they're both f of x. This is the function f of x. But what happens when I take the absolute value of it? Well, we know that if I take an absolute value of a positive number, it stays positive. So when I plug in the y-coordinate from this blue curve, positive y-coordinates will stay put. So if I have a point where y equals 2, that point is going to stay at y equals 2. And that's true for all of these values here. They're actually just going to stay where they are. Let me try to draw this carefully here. Good enough, right? Positive values are just going to stay where they are. That's true of these positive values as well, right? But these negative values, when I had negative y-coordinates, so if I plug them in here, I'll take the absolute value and they'll become positive. So I'm going to take this part that's below the x-axis and it just bumps and reflects over to the opposite side of the x-axis. So it's just going to look like this. I'm going to take the whole curve and reflect it over the x-axis. So you get this kind of weird W-looking thing, right? Or maybe like a tooth. So absolute value is like its own sort of form of transformation where you just take any values that are below the x-axis and reflect them up above the x-axis. Let's do one last quick example here where it says describe the relationships between the graphs of f of x and g of x. It doesn't ask us to graph them, just to describe the relationship. So let's identify the transformations that are going on here. We are subtracting inside of the function. To go from f to g, we subtracted inside of the function. So we have to subtract 2 before we evaluate the exponent. Notice this is an exponential curve. So this is going to subtract inside, which means we're going to move horizontally in the opposite direction. So that means go right 2 units. Then we negated outside of the function. So let's look at that real quick back in our rules. If we negate outside of the function, that's a reflection over the x-axis. So this means reflect over the x-axis. Right? So if we were to kind of write our answer out a little more neatly here, we could say to sketch the graph of g, of x, move the graph of f to the right 2 units, right 2 units, then reflect it over the x-axis. Okay, and this is how we can, this is when it says, like some of the homework problems are going to ask you to describe the relationship between the graphs, and this is how I would hope that you would answer something like this. The answer key in the textbook is going to look a little bit different, but something very similar, I'm sure. Okay, so there is how we can describe the relationship between 2 curves, just basically writing out the transformations. You could go ahead and graph those if you wanted to. It's a little bit tricky doing transformations on the exponential curve, but you'll get some practice applying the rules of transformations in the homework tonight, both drawing the graphs and then describing the relationships. So here are some practice exercises for you to be working on in your textbook on page 143, and that's our section on parent graphs and transformations.